Machine learning. You hear that phrase everywhere, and it sounds impossibly complex, right? But what if I told you the core idea is something you actually use every day? In the next few minutes, we're going to skip the dense textbooks, and we're going to build our very first machine learning model, step by step, to solve a real problem. Let's dive in.
Think about it. You see machine learning in action all the time. When your phone magically groups all the photos of your best friend together, that's machine learning. Or when your email just knows that an offer for a special prize is junk and sends it straight to spam. Yep, that's machine learning too. But how do they actually work? Well, these aren't just clever programming tricks. They represent a totally different way of thinking about how we tell computers what to do.
So what is that big shift? Well, traditionally, a programmer would have to write out every single rule by hand. A giant list of if this happens, then do that. So for a spam filter, it'd be like, if an email contains the words free money, then mark it as spam. Okay, simple enough. But what if the spammer writes cash prize instead? You'd need a new rule, and another, and another. It's endless. Machine learning completely flips this on its head. Instead of writing rules, we just show the computer thousands of examples of spam and thousands of examples of good emails, and we let the algorithm figure out the patterns for itself. This is the magic part. It allows it to generalize and make smart decisions on new emails it has never, ever seen before.
And this ability, this power to learn directly from data, lets us go way beyond what's possible with those old, rigid, hard-coded rules. It lets us tackle problems that are just, well, they're simply too messy and complex for a human to write rules for in the first place.
A perfect example is face detection. For years, programmers tried so hard to write the rules for what a face looks like. A face has two eyes, a nose in the middle, a mouth below that. But these rules failed all the time because of different lighting, weird angles, glasses, beards, you name it. It was a total mess. With machine learning, we just show the algorithm thousands and thousands of pictures that we've labeled face, and it figures out all those subtle, complex patterns on its own. It's a complete game changer.
So this type of machine learning we've been talking about, the one where we provide all those labeled examples, it's actually the most common kind. It's called supervised learning. And a really great way to think about it is like a student learning with a teacher.
In supervised learning, we are the teacher. We provide the algorithm with the study materials. So we give it an input, say a medical image, and we also give it the correct output, or label. In this case, maybe benign or malignant. We do this over and over again with lots of examples. And just like a student studying with an answer key, the algorithm starts to learn the general rule that connects the inputs to the correct outputs.
And this approach is just incredibly powerful. It's the same technique used to decipher that messy, handwritten zip code on an envelope. It's used to help doctors spot tumors in medical scans. And it's what protects you from credit card fraud by learning the patterns of your normal spending versus what a fraudulent transaction looks like. In every single case, the goal is the same. Learn from examples we already know the answer to so we can make predictions about the future.
All right, before we dive into our hands-on example, let's just quickly nail down two key terms you're going to hear a lot. First up is a sample. That's just a fancy word for one single data point or one row in our data table. So one email or one medical image. Easy? Second, a feature. That's just a property or a characteristic of that sample. Think of it as a column in our data. So for a customer, a feature might be their age. Samples and features. They're the basic building blocks of everything we're about to do. Okay, enough theory. Let's make this all feel a bit more real. Let's imagine we're helping out a hobby botanist, and she has a very specific problem. She loves iris flowers, but she has a really hard time telling the different species apart just by looking at them.
Now, luckily for us, she's collected a bunch of measurements from many different iris flowers. She's measured the length and the width of their petals, and the length and width of their sepals. Those are the little green leaves at the base. Crucially, for every flower she measured, she also wrote down its correct species. So our task is to build a machine learning model that can learn from her data to predict the species of a new flower, just from its measurements.
And this is what her data looks like to a computer. See? Each flower is a sample, which is just one row. And those four measurements, sepal length, sepal width, petal length, and petal width, those are our features. We're essentially translating the physical flower into a nice, neat table of numbers that an algorithm can actually understand.
Now check this out. When we visualize this data, something really cool happens. This is a pair plot, and each color on here represents a different species of iris. Just look at how they form these nice, distinct clusters. See, for instance, how the blue dots down here are totally separate from the green and red ones? This visual separation is a massive clue. It's telling us that a machine learning model should have a pretty good shot at learning the boundaries between these groups. This is a very good sign.
So seeing that clear pattern in the data is basically our green light. We've got our data, we have a clear goal, and it definitely looks solvable. So now it's time to actually build our digital botanist.
But hang on, there's a really critical question we have to ask ourselves first. If we use all of our flower data to teach the model, how can we be sure it actually learned the patterns and didn't just, memorize the answers? A model that just memorizes is useless in the real world. We need to know if it can handle a new flower it's never seen before.
And the solution to this is actually pretty clever. We split our data. We take a big chunk of it, say 75%, and we call that our training set. This is the data the model gets to see and learn from. But we hold back the other 25%. We lock it away and call it the test set. This data is kept totally separate, and we use it at the very end, like a final exam, to get an honest, unbiased grade on how well our model performs.
This gives us a super simple, repeatable 4-step workflow. Step 1, split the data, just like we talked about. Step 2, choose a model. We're going to use a really intuitive one called K-nearest neighbors. I'll explain it in just a second. Step 3, we train the model on our training data. And finally, step 4, we evaluate its performance on that test data we kept hidden.
So how does this K-nearest neighbors thing work? Honestly, it's brilliantly simple. When we give it a new, unknown flower, the algorithm just looks through all the flowers it saw during training and finds the one that is the most similar, based on its measurements, its nearest neighbor. And then it just predicts that the new flower is the exact same species as that neighbor. That's it. It basically learns by memorizing the training examples and makes predictions based on similarity. All right, we've split the data, we've chosen our model, we've trained it. Now for the moment of truth. It's time to see how our little model did on its final exam, that test set it has never ever seen before. So we're about to ask our model to predict the species for every flower in that hidden test set. Then we're going to compare its guesses to the true answers. How well do you think our simple little model is going to do? 97%. Wow, that is an absolutely fantastic result. Our model, just using that simple logic of finding the closest neighbor, totally passed its exam with flying colors.
But what does a number like 97% actually mean? Well, it means that for all the irises in that test set, data the model was completely blind to, it correctly identified the right species 97% of the time. This proves it didn't just memorize the training data, it actually learned the general patterns. It can generalize.
And just like that, we've done it. We've solved our botanist's dilemma. We went from a real-world question to a table of data, and then to a fully trained model that can act like a digital expert, identifying iris flowers with a really high degree of confidence.
So there you have it. That's the entire life cycle of a basic machine learning project, from a simple question all the way to a working model. We used a simple process and some data to teach a machine to be a pretty darn good botanist. It really makes you wonder, doesn't it? What other experts can we teach a machine to be? A radiologist? A financial analyst? Maybe even a music composer? The possibilities are just getting started.